I'm looking forward to the discussion today and to tell you a little bit about some of the challenges in data centers that pertain to energy efficiency and our future needs. So let me go ahead. There. So this is a view inside one of our data centers. And I thought I'd start by showing some of the things that happen inside a data center, some of the functions. So obviously there's a large compute function. There's a lot of data. This is all the, if you are active on Facebook or Messenger or WhatsApp or Instagram or any of our applications, there's a lot of pictures, videos, chat that needs to be stored. So storage is a large part of the infrastructure inside a data center. As we do that compute function, we need memory, obviously, to be able to manipulate that data, just to be able to get it to the right place at the right time and do backups and that kind of thing. And then one of the largest growing areas of our data center infrastructure at the moment is AI ML and video transcoding. This is so that we have, just to describe what that really means. So video transcoding is needed so that no matter what device you're using, no matter what your internet connection bandwidth is, you're able to have a fluid experience using the apps, so that the videos and other multimedia you're using is at the appropriate resolution and takes a reasonable time to download. And all of that, as you can imagine, is incredibly complicated, and we have been investing heavily in that area. Again, in AI ML, a lot of the way that these applications work requires us to, well, first of all, for security reasons, that we need to know to protect people and make sure that we're not putting inappropriate things out there. So that requires some AI. And then you can imagine ranking and recommendation, which is a lot of how the platform works, is a very big user of AI ML. So that's what's happening in the data center. It's all connected together with the network. And that's going to be the topic in the afternoon, where we talk about photonics, because our network is largely a photonics network, and opportunities for energy efficiency there. Yeah, so moving on. So I did touch on AI ML as one of the largest growing areas in our infrastructure. And this chart is from the literature. This is some data that was collected by the group in Berkeley. And it's just interesting to see how fast this is growing. And it's representative. You're going to see some more detail as we go through the talks today. I know I'm not the only one hitting this point, but I like this chart because it includes Moore's law. And I think we're all very familiar with Moore's law and the journey we've been on. Factors of 2 in 2 years. It seemed like a really good journey, and then it just is dwarfed by the growth that's going on. If we look at computer vision and natural language processing, speech, that's the blue line, and that's on approximately 50 times growth every 2 years in terms of the model size and complexity. But I think the one that catches everyone's attention is this more recent trend, and it's in red here for good reason. This rings alarm bells lots of places. Phenomenal growth, 750 times in 2 years. It's just hard to comprehend that. So this is the transformers, deep learning. As I said, we'll get into more of this as we go through the session this morning. I think that's going to be a very interesting discussion. So Meta is just at the beginning of our journey. So I showed some very large growth rates. If you look at this chart, this is just our inference, which is small compared to training. And we're really just getting started. So here, and this looks very modest, right? 2 or 3 times growth over 2 years. So what is, why, what, right? How does this touch the infrastructure? I thought I'd start by just going through training and the process that training follows. So we start with data, and obviously there's a lot of data in our data centers. You need a lot of data to make the model, the quality of your results depends on the amount of data you use. So it all starts with data. And then a set of features. This is defining what the model is going to do and the boundary conditions set up around that model. The model is then trained, and then the results are evaluated, and there's a feedback loop here. This is one of the feedback loops that needs to be accelerated. This is something we call developer velocity, and it's the speed at which you can iterate through your models. So this is an important loop. And then as the model goes through that development and then it gets deployed, obviously there's multiple generations of this. So there's an infrastructure loop. So we can think of this as a software loop and a hardware loop. And that's an important point because it leads to, how do you keep up with these tremendous rates of growth? And it's by using these 2 loops efficiently together. This is hardware, software, co-design. I'm seeing thumbs up, so I think I'm having some internet issues. I'm just going to keep going. So it's working at the moment. So some of the strains that this accelerated innovation puts on our infrastructure is illustrated here in the purple boxes and the purple lines. There's a challenge with storage just because there's so much data that needs to be stored and it needs to be connected to the features. There's a challenge in the network because that's a lot of bandwidth that needs to be moved around. And there's a challenge in the compute and memory because it's a lot of data that's being computed, a lot of memory that needs to be accessed, and latency requirements to make that go fast. So speed of innovation is key here. And I said already, software, hardware co-design is really how we get ahead of this. So let me talk about another area where we're able to move fast, and it's a dimension of flexibility. And we get flexibility by breaking the problem down and configuring it in different ways. So this is an example of how we do that in hardware. So this is the hardware design. We're already seeing disaggregation, so breaking a problem down in logic, in compute logic. We've already, the industry has already been doing multiple cores and breaking down large chips into smaller pieces in that environment where everything is the same, just more pieces. We're now looking at another level of flexibility where it's functionality. So we're choosing which chips or chiplets are done on particular nodes, and that adds more flexibility. So you'll see the colored blocks change shape as they are implemented on different hardware solutions, different semiconductor solutions. And there's examples in the industry that we can point to where this saves cost by improving yield. This is a particular example from AMD, where the chips are getting so large that yield impacts cost. If you build a very large chip, yielding that full chip, that full die, becomes difficult because the defect density becomes an issue. So if you can partition that large chip, create chiplets, as you see shown here, the defect density means that there's less defects per chip, and so that helps with yield. Again, there's a number of these different examples. This is happening in the industry already, but it's something that we can leverage here. So I'm pointing to this afternoon's session with Optical Interconnect as an example to build on from here, where once you're using chiplets, because of all the, the flexibility and the improved yield and the ability to scale faster, how do you put those chiplets back together? How do you connect them together again? And this is an opportunity for photonics, because these are high bandwidth interconnects, and as we move up in bandwidth, it becomes more power efficient at some point to use photonics. And we'll talk more about what that point is. I'm sure that'll be an interesting discussion. So here's some examples. The left-hand side, this is some examples in the network, how you could use optical interconnects in the network to connect things together. And I'm sure we'll be talking more about that today in this afternoon session. And compute I/O, the computational systems have very high bandwidth connections too, and there's opportunities to use photonics there. So that will be very interesting. Why I point to network, I think we have some interesting data here which indicates why this is an area to focus on, particularly because of energy efficiency and reducing power consumption. The chart on the left, you can see how, despite our best efforts to reduce the power per unit bandwidth over time, just the amount of bandwidth that the network needs is increasing exponentially. So of course those two don't offset each other. So we're looking at a net positive increase in power, which is obviously not desired. And this we see over generations in our data center. If I build this out, oops, too far. If I build this out here, we see, sorry, there's some lag. Here we go. We see that not that long ago, 2012, the network, in terms of power, percentage power didn't show up as a considerable usage. And that has significantly increased. And where the rate at which it's increasing is alarming. So this is something that we need to do something about, for the reason is because of the chart on the left. We will talk more about that for sure. And one way that we're looking at solving part of that power problem is through integration. And this is an evolution of optical interconnect as we see the path forward, moving from pluggable optics through midboard optics to co-packaged optics. And you can see the level of integration increases at every generation, to the point where we can actually remove a lot of the energy that gets wasted in interfaces by having a very compact solution. And this is work that we started a couple of years ago, and you can find out more about it at the co-packaged optics link that's listed here. So I'd like to leave some time for questions, so I'll summarize here some of the areas that would be useful to collaborate further on. The first one is design for high volume. This is something that all the hyperscale data center users have in common. It is a very high volume, and I'm talking about unit volume and scale things. It's a lot of pieces, and it's growing fast, and that's common to all of the hyperscalers. So designing for that environment is very important. There's a lot of leverage to be had there. To reduce power through chiplet integration, I think that the evolution that I just showed is a piece of this solution. And I'd like to encourage collaboration to build the ecosystem. There's a lot of different moving parts and pieces of the puzzle, and if we work together, I think we can create a very strong solution. So that's all I had in my talk. I look forward to some questions, and I've shared my contact information here as well, and I'm available for follow-up afterwards. Thank you.
Thanks, Catherine. Any questions from panelists or on the chat?
There is one in the chat too, John, when you get to it.
Okay, from Johannes, are there any approximations or estimates about the share of AI/ML related to overall compute?
I don't have specifics to share on that, but as we get into the discussion, there's going to be a panel on AI/ML, and that might be an opportunity to dig another layer into that. I'm going to stop sharing so I can see people.
Okay.
Yeah.
Well, demand you showed is indeed very scary. I don't know if that was your second slide roughly, but the need for this is huge. How big of impact can we have? If everything, you know, all the disaggregation, all the optical interconnects and all the improvements in learning happen, do you think the share of electricity going to data centers will remain constant or go down? Or do you see it continuing to increase?
I'm a realist. I think that's an ambitious goal, but the trend, if we just extrapolate from where we are today, of course, that's completely unsustainable. So there's two extremes there. I think the goal is clear, the target is clear. How close we get, I wouldn't like to say.
Okay.
So there were a couple questions in the chat.
Why don't you guys read them? I don't see anything else.
So from Neil Anderson, in current state-of-the-art data centers, what fraction of the total consumed energy is consumed at the chip level for compute plus memory? And how do you expect this fraction to change going forward?
Oh, that's such an interesting question. It's one of those questions where it sounds so simple, doesn't it? Like we must have a metric for that. And I'm trying to slice through a number of different areas in our data center to try and get to that sort of nice rule of thumb. And what I'm coming to is unfortunately, it's all very complex. I don't have a good handy rule of thumb that I can pull out to answer that question, but I think I'm enjoying the question. And I think that would actually be very useful for some of the collaboration discussions. So thank you.
One of the questions was about, will your slides be shared later? So I'll just make a global answer first, which is if the speakers are willing, then we will post the slides. And again, I think most speakers have agreed, but so this workshop is being recorded and we'll put the presentations out on UCTV. Again, as encouragement to all the panelists to allow us to do that. We typically find, like the last workshop, the downloads from UCTV end up being tens of thousands and even more than that in a couple of cases. So it gets a much broader impact at that point. So, and Catherine, so I don't know if you're willing to share these slides. The question was directed to you, so I'll pass that on.
So the first thing is, indirectly, the slides are shared. The session is recorded, so so the slides are there. Sending them, I'm going to see what format I can share them externally. That's usually where we have challenges. But for sure they're available if you rerun this session.
Great, thank you.